gradient with respect to theta. So, well, in order to calculate gradient with respect to theta here, I just need to calculate gradient with respect to theta here. Let's calculate gradient with respect to the first index of that. Let's do this, guys, here. Because gradient, I need to calculate partial derivative with respect to all the parameters. Calculate the first component down. So that would be equal to 1 over m. Summation of j goes to 1 over m here. I need to calculate what's the partial derivative of these overall functions here with respect to the first component of that. So that would be theta dot xj minus yj, and then take a square of that. So that's what I want to calculate, this quantity of that. This function, and what is the gradient of this function with respect to theta? And we're going to apply the so-called chain rule from the calculus, because this is a quadratic function. First of all, in order to calculate this partial derivative, I first calculate with respect to this square function here. And well, if I do that, that's equal to 1 over m. Summation stays the same, j to m here. And then I'm going to plot two terms here, because the square of that. And then and it will be theta times dot xj minus yj. So this is square terms of that. Right? Remember that? Derivative of dx squared over dx is equal to 2x. So that's what's written down here. Okay, and then because this guy here is a function of the parameter theta. So first of all, apply to outer function. Next will be the next function here. So that would be what's the partial derivative of theta dot xj together with respect to theta 1. Okay, so which means that I just need to evaluate this quantity of that. But now you can think about this. What is the theta? Let's look at here. What is theta dot xj? So that is linear combinations of the parameters. Theta 1, j sample, first component of that. And then theta 2, j sample, second component of that, and so on. So now I want to do partial derivative of these guys here with respect to theta 1 here. So I'm going to partial derivative these guys here respect to theta 1, the first one here, partial of these guys here respect to theta 2, and so on. But you can see what is the first component here, that is simply x1j, because it's just, theta 1 times a number, right? x1 and superscript j here. What about the second term here? The second term here is this guy's here, this is the theta 1 here. Second term you can see, because I'm going to take, what I'm doing here is taking partial derivative with respect to theta 1. I'm going to view all the theta 2 does not change. You can see this function here is not a function of theta 1, so therefore this guy is 0. And all the rest of them are 0. So you can see only remaining term is x1 superscript j here. So that is this term I'm calculating here. So if I write down that, you can see this guy here was simply equal to, if I erase this part of that, summation j equal to 1m of 2 here, theta dot xj minus yj. The only terms remain here is theta j times the first component of that. You can see that, right? So that's it. So you can see this is for the gradient with respect to theta 1. The only thing put here is this. So this is the same here. It doesn't depend on the index of 1 here. This is simply the difference. If I rewrite this term here, the first index here is simply 2 is a constant here. Simply the prediction here of the j sample minus actual observations here. And this is the error terms here, the residual, times this xj and the first component of that. And the first component corresponds, because I'm calculating the partial derivative with respect to theta 1. And you can see that if I do partial derivative with respect to theta 2 here, and then the terms will be exactly look similar to the ones I just did. 2 here, and then the error term is the same. That will be j samples of that. The only thing different here is instead of doing xj subscript 1, I'm going to do subscript 2 here. and so on. And that is gradient. How do we calculate gradient in respect to the MSE function there? And I can write those guys here in a more compact form. So I suppose I'm going to write them this way. Partial derivatives, this guy here, respect to theta. I treat this as a vector here. So which means that the first component is partial L respect to theta 1 here. And the last component is partial L respect to last component. So it'll be theta n here. And put together as a vector. So that's what we intend to do. It's going to represent these guys here as a gradient vectors for that. And you can see all the things here are the same. The only thing different is this guy here. As a result of that, you can see this is simply equal to 1 over m. Summation of j goes to 1 to 2. I can put 2, move 2 here instead of here. And then next will be the difference of j sample, prediction here, minus the actual observations of that, times x, j samples. And that's it. And let's look more closely here. This is the error terms. And this is the input vector of the j sample there. And essentially, if you look at the loss of one sample here, if you focus on loss of one sample, and then the gradient is simply something like this, the prediction minus actual observation, okay? And then times the input vector x. And that is the gradient vector for calculated based on one sample, x, y here. And of course, you have 2 in front of that, okay? That will be 2 because of the square terms of that. But in general, the forms here is pretty easy to memorize or understand. Essentially, gradient is simply say, you know, what's the is my prediction greater than the actual observation, which means is this residual error is positive or negative. So that signs of the error terms here will determine you the direction I need to change my parameter theta. So think about this way. Suppose, let's just make a simple assumption. Suppose for now, your x, all the components of the x are all positive. Let's just make that assumption. And so under this assumption here, suppose your actual prediction is greater than the actual observation. So which means y hat is greater than y. And which means you're overshooting your predictions. So, right? Because your prediction is bigger than the actual observation. So y hat minus y is positive. So as a result of that, this gradient here is a positive vector. So now the updated direction will be the negative of the gradient will be all negative numbers. So which means that because your current theta is shooting too large, as a result of that, you are overshooting your predictions. Your prediction is bigger than the actual observation. So the right way to do is to reduce the values of those parameters. And if I say taking the negative of the gradient, that will essentially achieve my goal, because in that case, the delta theta, the update of theta here all points to the negative values, which means that if I do update, the values of each individual component of theta will decrease. And so that seems like it's consistent with what we are trying to do. And similarly, on the other side here, if your y hat is less than y, which means you're under predicted, and your predicted value is smaller than the actual observation. So the gradient will be negative, and the opposite gradient will be positive. And then as a result of that, you will increase the values of theta, and you boost up your prediction. So you can see that's somewhat more consistent with that. So that's it. So that's where how do we calculate the gradient of the loss function with respect to the parameters here. And this is based on one sample only, and this is based on the combine all the samples. In the end, I updated parameter based on this gradient calculations of that. So sometimes you can see there's terms of 2 here. And for these reasons here, in general, in many cases, when people calculate MSE, they might put a 2 in front of that. They do 1 divided by 2m instead of m. The purpose of introducing this factor of 2 is this. Once I have 2 here, I can get rid of 2 here. So in that case, the gradient was simply y hat minus y times x. So that's just by convention. If we do that, and then your loss function will look something like this without 2 here, and that will be simply 1 here. And then the term seems like cleaner. So I don't know if it's cleaner, but just convention many people do that. So as a result, if you follow this convention, your gradient will be simply y hat minus y times x for one sample. And then you average across m samples here, that is the gradient of the entire loss functions. So that's for the gradient calculation there. So there's another way of, so right now for the gradient calculation, I average over all the samples there. So there's another way of representing them is through this matrix